Okay, class, welcome to your distanced learning session. And today we will be talking about a subject near and dear to my heart, electricity. Okay, so where to begin? We will begin with our class mantra, which is that all matter is made of what, class? Atoms. Everything's made of atoms, and the outside of the atom has a negatively charged electron, and the inside of the atom has a positively charged proton and any given number of neutrons depending on the atom. So we don't need to concern ourselves with the neutrons, but we do need to concern ourselves with the protons and the electrons. We remember that electrons are charged with a negative charge, which is just a convention. Doesn't really, if I would have done it, and a lot of people agree with me, we should have labeled them electrons as positive and protons as negative, because it would have made currents simpler. But we'll get to that. So anyway, electrons are negative and protons are positive. And so who can tell me what happens when you put a proton and an electron near each other? What do they want to do? Andre?
They want to come closer together.
Yeah, they attract each other, okay? What happens, Thaddeus, if I put a proton and a proton next to each other? They're going to go apart. That's right. They're going to push each other away from each other. And same thing, if we do an electron and an electron, they will also repel one another. Okay, real simple. Now, there are different ways that these charged particles interact in different materials. Generally, we classify them into two broad categories, but there's really a great deal in between. We talk about who knows what we call materials that conduct electricity? What do we call them? Conductors, right. We talk about conductors, and who knows what we call things that don't conduct electricity?
Non-conductor.
Well, you could call them that, but there's another. Insulators. Or, insulators is kind of the common parlance. Insulators. But really, we could also call them dielectrics. Hold on a second. It's not Dianetics, and it's not, anyway, it's dielectrics. Dielectrics. Okay, it's just the more physicsy term for an insulator. Now let's talk about what are some things that are conductors. Who knows? All right, metals. All metals. If it's a metal, it's a conductor. What's a good example of an insulator? Rubber. Good. Rubber. What else? Carbon? No, carbon's actually a conductor. I'll use black because carbon is black. But not all forms of carbon are conductors. What would be a form of carbon that is a conductor? Any idea? Anybody? Lead is a metal. Well, carbon steel is just an alloy of steel. But graphite, a pencil lead, quote unquote lead. Oh, okay. That's what you meant. A pencil graphite is carbon, and it's a conductor. What's another form of carbon that you can think of?
Plastic.
Carbon. Well, okay, a hydrocarbon is a plastic, and a plastic is definitely an insulator. But there's a form of pure carbon that's an insulator. Diamond.
Pure carbon.
Yeah, pure carbon insulator. And it, huh? Oh, I'm sorry. You're right. Wrong category. Diamond. Diamonds are insulators. Now, let's take glass for example, which is glass is just molten, or it's silicon which has been melted down. Is an insulator. But when it gets hot, it becomes a conductor. So, for example, if you take glass and you heat it up with a torch, and then immediately while it's red hot, put it in the microwave, it'll keep getting hotter and hotter and hotter because it becomes a conductor, and then because it's a conductor, the microwave can heat it. So it's a great way to melt a lot of glass if you ever want to do that.
Heat it up first.
Heat it with a torch, and then put it in the microwave and turn it on.
Wow.
That sucker is going to get really hot. Pretty neat.
And it's not going to work if you don't heat it up.
If you don't heat it up first, it'll never work. So, but molten glass is a conductor. Molten glass. Now, there's also a very broad there's another category, which we'll talk about this in a little bit. Okay, so we've got conductors and we have insulators, generally speaking. Let's talk about at an atomic level why they are the way they are. Okay, hold on, everybody. All right, so let's look at our atomic model of our material, and let's do a metal. So you have a whole bunch of positive nuclei distributed throughout the material. And likewise, you have an equal number of negative charges throughout the material. But in a conductor, everything is covalently bonded. What do we know about covalent bonds? Yes?
The atoms actually share the bond.
Yeah, they're sharing the electrons, okay? And they're sharing them in such a way that this electron is free to travel to this atom, and to this atom, and to this atom. It doesn't necessarily have to loop around all of them, okay? But it can move freely, and indeed it does. That electron does move freely among all those adjacent atoms. So you can get an electron from one side of the metal to the other, okay? The atoms themselves are actually fixed in place, though. Why?
They're nucleuses, right?
Yeah, but why can't they move? If you get it hot enough, they do start to move. Okay, kind of a mystery. Oh, it's something to think about. But the positive nuclei are in a metal are fixed in place unless it's molten. Then they can move as well. Yes, Nicholas.
But each positive charge has to have one electron at all times, right?
Yes, it has to be balanced.
So then do they all move at the same time? Do the electrons move around?
Yeah, all the electrons move at the same time. That's a good point. I mean, you can get a higher charge density in one area just due to thermal fluctuations, but not very much. Now, let me just give you an example of how powerful these electric charges are. Because let's make a new page. Let's talk about this. This is something to recognize how powerful this force is. Let's say you have a head of a pin. This is greatly magnified head of a pin, right? And it's filled with millions, if not probably more like billions of metal atoms in this head of the pin. Yeah, it's going to be billions, if not trillions, of metal atoms. Probably just billions. Okay, we get the idea, right? And each one of them has an electron. I'm just going to abbreviate because we'll be here all day. Okay, those are all our electrons. If you were to suddenly, if you had a machine that could do this, suddenly eliminate all of the protons. So you just get rid of all the pluses. I can't do this very well on the board, so I'll just do it like this. So you got rid of the pluses, you get the idea. And now it's all just electrons. That thing would blow up with so much force that it could lift an aircraft carrier into outer space. That is how powerful the repulsion of electric charges is.
That's the head of a pen?
That the head of a pin.
Oh,
Same thing. I mean, it's just a little teeny point. That's how strong all those charges are. Likewise, if you got rid of all the electrons and it was just the protons, it would do the same thing. It would just, you could literally, it would blow up with that much force. It's like a nuclear explosion. Okay? That's how much force is in there.
is there any way to do that?
Is there any way to do that? No. Because you'd have to put all that energy in there to separate them. Because just like it would blow up with that much force if you got rid of the positive charges, to pull those charges out, you need that much force. Okay? We'll go on to the next lecture. Okay.